Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video rounds out a review of functions for a college algebra course in mathematics. So we are now in the midst, or actually at the end, of inverse functions, and we're going to talk about the graphs of inverses, specifically how to find the graph of the inverse of a function. The title of this is slightly misleading. It says finding inverse functions and their graphs. It really should be finding the graph of an inverse function. So the how-to on this, again, assuming that you've had Algebra 2 in the past, there's no reason for me to build the theory behind the scenes here anymore because you've had that. So this is just a review. To graph the inverse of a given one-to-one function f, there are a couple choices. You could either graph your function, the original function, and reflect that about the line y equals x, or you could plot the points x, y that occur on the graph of f in their opposite order. And that is because the values of x and y swap when you're dealing with the inverse function. Now, there are complications to this. For example, you might have to domain restrict a function f to make it one-to-one first. And this is our very first example. This is just what we're facing here. So we're going to use Desmos to draw a graph of this function f of x equals the cubed root of x squared plus 1, because that's not a function you would be expected to graph by hand. And then if f is one-to-one, which it will not be, I'll just give you a heads up right now, we're going to graph its inverse. Well, since it won't be one-to-one, we need to restrict the domain of that function and graph the inverse of the resulting domain restricted function. End all be all is just graph the inverse of the function that it's been stated. And if it's not invertible, force it to be invertible. So here you're looking at a graph of that function on Desmos, and you can see that there are y values, for example, this y value right here, that also occur twice on this graph. In fact, you can see there are these two y values specifically, the y value of 1.26. It leads back to two different x values, -1 and +1. So therefore, this function is, while it is a function, it is not one-to-one because you have a couple y values, or I'm sorry, a single y value that leads back to two different x values. And you can see that's the case for all of these y values. And I'm just creating a line here, but you can see that everywhere this horizontal line strikes that curve, it strikes it at a y value where for that y value, 2.25 in this case, there are two x values that lead to that. And so again, this is not a one-to-one function. So what I would like to do is domain restrict this so that we get a one-to-one function. And you can see if we start erasing from the left-hand side here, we get to this point right, let's just say we only erased up to that point. Let's just pretend. Is that a one-to-one function? Well, turning that line back on, you could see that there are still some y values, specifically the y value of 1.24, that lead back to two different x values. So again, we need to do some extra erasing here. So we continue our erasing until we get to roughly about here. Now, at this point, you could see that from that point forward, our y values only come from a single x value. So this y value right here only occurs once on this curve, and it leads back to a single x value. So therefore, this function looks now to be 1-to-1. So let's go ahead and domain restrict our function to start at x equals 0 and go on to infinity. I'll just go ahead and write that in here. So we're going to let, oops, except I need to use a different pen there. So we'll let the domain of f, that is domain of f be 0 to infinity. Again, we could have chosen the domain to be negative infinity to 0, actually. That would have worked as well. But I personally like to have positive x values in my domain. So that's a personal choice. You're not forced in this problem to choose any specific domain. And in fact, you could have tightened up the domain even further. They did not say anything about the largest domain that is 1-to-1. All they said is, hey, erase as much of that graph as possible so that you get a 1-to-1 function. And had I just continued erasing, this is still 1-to-1. So I could technically, let's say I erase up to 4, I could technically have said, oh, let our domain of our function go from 4 to infinity. That's still 1-to-1. That's perfectly fine. Now I'm going to do a hybrid of moves here because I want you to see how to do this by hand, and I also want you to get a strong visual. So what I'm going to do is graph that function from 0 to infinity on my paper here. Now that's a fairly decent representation of the graph of f. It's not the greatest, and if this was a base graph for example, like an x squared or an absolute value of x or something like that, if it was a popular function that we are very, very familiar with, then it should be more accurate. But for right now, I'm really just copying this from technology, so there's no real reason for me to sweat it being slightly off, to be honest with you. But now we have two ways to graph the inverse. One way to graph the inverse is to graph the line y equals x and reflect that curve about that line. The other way to graph the inverse is to swap the x and y values. Now, swapping the x and y values here is actually going to be somewhat of a pain, because if you build a table of values, you can see that the numbers are not beautiful. They're not really easy to plot as far as the y values. And so if we swap the x and y values, it's not really going to be great. So the best thing to do here, I think, is to draw the line y equals x, which requires us, in a way, to know where these values cross. So luckily, I have 0, 0. I'm going to draw this line in red. We have 0, 0 right here. Y equals x goes through 0, 0 and 1, 1. So I know that I could at least do that. Plot those points there, and then you could just connect those two dots with a line. Now, I'm not going to do a straight edge here. I hope you don't mind. I'm just sort of trying my best to do this. In fact, maybe I'll pause while I do this. There we go. That's the line y equals x. I know it's the line y equals x because it goes through 0, 0 and 1, 1. That's what this point is right there. Now all I need to do to graph the inverse is to reflect this black curve about that red line y equals x. This takes a little bit of skillful artistry, to be honest with you, and even though I'm a mathematician, I have a very hard time with visuals. So I need to take my time here to do this. So the way that I did that is I essentially viewed y equals x as a mirror. The distance between y equals x and that point should be the same as the distance between y equals x and the symmetric point over there. So that was my mirror move, if you will. And then I did the same thing for these 2 points. The distance between the mirror and that black point right there should be the same as the distance between the mirror and the blue point. It is a little bit of a kind of a messy way of graphing. So now I'll do the same thing on the other side here. So I had a little black point right there. That distance should be about the same. And then it should eventually go through 1, 0. So it should look like this. So I'm going to go ahead and maybe just do that. Notice I try not to go over my point. I try to leave an open space there so I don't draw over my point. But this would be, the blue graph would be the graph of f inverse of x. That's a nice way to graph inverse functions. The other way to graph, honestly, if you're handed a nice clean graph of f, is to plot the points in reverse order. But again, looking at this table of values, plotting those in reverse order would be just terrible because, again, you're approximating what the cube root of 2 is, what the cube root of 5 is, what the cube root of 10 is. You're probably better off just to kind of chicken scratch that out. So that's a good way of graphing an inverse for a given function. Just a quick check to make sure I didn't miss anything else on the problem. So using Desmos, draw a graph of f, and then if f is 1 to 1, graph its inverse. Okay, so that's what we did. We didn't use Desmos, by the way, to graph the inverse. We could have, but we didn't. But just to showcase that we are correct, you can see I did actually graph them here in Desmos. If you're wondering how I quickly graphed the inverse, is the way I did it was, actually, let me scroll over to show you. So there's my function right there. This is actually how I control the domain restriction. As I just said, x goes from, is greater than or equal to a. But I'll remove that so that's not a confusion, just so that we have a look at the actual function. So our function was f of x equals x squared plus 1 to the 1/3 power. The y equals x is the line we're rotating about. And then the inverse, all I did was trade out, let's call this y. I traded out or swapped y for x. That's all I did. So this ends up being x equals and then a y squared plus 1 rather than y equals an x squared plus 1. That's how I graphed the inverse. Swap the x and y values. That's it. Remember what I said earlier in the previous lecture about the reason why we swap those variables is so we can graph. That's the only reason why you swap variables with inverses, is so you can graph. Now we finally arrive at the pretty much the last item when you're talking about inverse functions, specifically the horizontal line test. Now, most people actually know this, and I've alluded to it many times in the lectures on the inverse functions, but now we're officially stating it. A function is 1 to 1 if and only if any and all horizontal lines intersect its graph at most once. First, as a reminder, if and only if is often written as IFF. So that's just an aside. And to give you a visual of this before we go to prove it, if I gave you a function that looked like this, which it is a function, what the horizontal line test is saying is that if there exists a horizontal line that strikes this curve more than once, we've got an issue. Now, of course, it's not worded that way. The way I word it is, this is a 1-to-1 function if any line, horizontal line that I draw is guaranteed to hit it at most once. Well, that line hit it at most once. Oops. This line hit it at most once. This line hits it at most once. But those aren't every single horizontal line in the world. Here's a horizontal line, and it hits it 3 times. And so therefore, since it hits it more than once, we can throw this function out. This is not 1-to-1. That's the notation for 1-to-1. One that throws people off, so let's give another example here. Let's suppose that I give you this. That's our function. Let's just say this is the x-axis and that's the y-axis. Remember, the condition to be 1-to-1 is that every single horizontal line I can draw will hit the graph at most once. That at most is very important because think of numbers that are at most 1. 0 and 1. Those are two integers, actually, two whole numbers that are at most 1. 0 and 1. Well, here's a horizontal line. Sorry that is skewed. I just drew that kind of sideways. There's a horizontal line. It's parallel to the x-axis. It doesn't even hit the curve, but that's okay because it hits the curve 0 times, which is at most once. Remember, 0 is less than or equal to 1, so that works out. Here's a horizontal line that hits the curve at most once. Here's another one, hits the curve at most once. Here's another one that hits the curve at most once. No matter how many horizontal lines I draw, each of them will hit the curve at most once in that case. So this is 1 to 1. So you get the idea, hopefully. So let's go ahead and actually prove this theorem. So the way this works, because it's an if and only if and only ifs work like this. Maybe I should say non-if and only ifs work like this. So suppose that it wasn't an if and only if. Suppose it was just if P, then Q. P is what we call the precedent and the Q is the antecedent. So suppose that somebody said, hey, you can assume P is true. If P is true, then Q must be true. Well, that's the general statement for most theorems. However, if and only ifs work both ways. So they work not only if P is then Q, but also if Q, then P. For example, something that is not an if and only if. If it's raining, then it's cloudy. That makes sense. If it's raining, then it's got to be cloudy. The opposite is not true. If it's cloudy, it does not actually have to be raining, right? So that is not an if and only if. All right. But there are other if and only ifs. They're hard to find in the real world, honestly. Or at least I shouldn't say hard to find, but they're not as common as the first type. But this is an if and only if that we're dealing with. And when you prove an if and only if, you have to prove it both directions. You have to prove, well, if the first thing is true, that a function's 1 to 1, let's prove that all horizontal lines intersect its graph at most once. And then once you're done proving that, you have to go backwards. You have to say, well, now let's assume that all horizontal lines intersect the graph at most once, and we'll prove that means the function has to be 1 to 1. That's how an if and only if proof works. By the way, if you're wondering why you're seeing proofs, it's because you're in college level mathematics probably. And so that's what you have to do. And you also have to be able to prove things. So let's go ahead and just get your proof skills primed. It's not that I'm going to say on an exam or that your instructor will say on an exam, prove something like this. But it's good to see proof so you can start wrapping your mind around how to structure a proof. So here we go. We'll start the forward direction, which means we're going to assume or suppose that F is 1 to 1. And we'll want to prove that therefore any horizontal line must strike its curve or the graph of F at most once. Now, when you do a proof, you should always reach back into your bag of definitions and theorems. F being 1 to 1 implies something by definition. So I'll say then, this is by the definition of being 1 to 1, f of x, well, that's equal to y, is true if and only if f inverse of y is equal to x. So let's see, we have that f is 1 to 1 because we get to suppose that. That's the very beginning here. A function is 1 to 1. And using the definition of f being 1 to 1, we know therefore that y equals f of x. Well, that's true if and only if f inverse of y is equal to x. Well, that's as far as we can get. So let's see where we want to arrive. We want to arrive that any horizontal line intersects the graph of f at most once. So we definitely want to create a horizontal line. And the equation of a horizontal line is y equals some number, right? Some constant. So we're going to go ahead and say, well, let y equal k, where k is just some constant. So is an element of the real numbers that So there are two notations here that you should be familiar with. This, what looks like an E, means is an element of. It also means belongs to or is in. And this capital R with a double bar on it means the real numbers. So you should know that. So this is just saying that we're going to grab a number k that's in the real numbers. I didn't need a parenthesis on there because I didn't have one. And I'll finish out my sentence. So let y equal k be a horizontal line. There we go. So now we're starting to build into where we want to arrive, right? We want to arrive at, we have a horizontal line. No matter what that horizontal line is, it has to strike the graph at most once. Well, let's find out if y equals k, that horizontal line, strikes the curve y equals f of x at most once. Well, if k is in the range of f, which means that k is an output of f, well, then we happen to know because f is 1 to 1, this must be true. Specifically, that if k is in the range of f of x, that k, oops, that was not supposed to be a highlighter, that k is equal to f of x for some value of x. But that's true if and only if f inverse of k equals x. The important part to know about that statement is k is in the range of f, so there is an x value that leads to the y value of k for the function f. But because f is 1 to 1, f inverse of that output k leads only back to 1x. So that is, that y value only gets led to by one value of x. Let me graph that off to the side just to showcase that. So you have some function where you're plugging in some x value. I don't care what the function actually looks like. It leads to a height of k. It can't lead to that height of k any other time. If it did, then f inverse of k would lead to two possibilities. And that's not how functions work. F inverse is a function. It can only lead to x once, right? Each input leads to a single output. So therefore, we know that as long as k is in the range of f, then, well, y will equal k only once. And so f intersects y equals k only once. Now, what if k is not in the range of f? Well, that's an easy one. If k is not in the range of f, then f of x is never equal to k, right? Because k is not in the range of f. There's no x value that leads to k. And so f never will intersect y equals k, the horizontal line. So in either case, your horizontal line intersects the curve either 0 times, in that last case, or only once. So it intersects at most one time. And that is just assuming that f is 1 to 1. So all of that leads to any horizontal line will intersect f at most once. Again, that's assuming that f is 1 to 1. So we have just proven the forward part. We've proven that assuming f is 1 to 1, well then, all horizontal lines intersect f at most once. Now let's suppose the other way around. So let me erase my highlighting here, and we're going to suppose the other way around just to finish out the proof. So we're going to go ahead and suppose that any and all horizontal lines strike f at most once. So let me bring you back up to the theorem. Now we're working on this. Suppose all this is true, and we're going to work our way backwards and hope that we can arrive at the fact that f must be 1 to 1. Let's go ahead and do this. Now, in this case, supposing that any and all horizontal lines strike f at most once, it involves a little more creative thinking. We'll start by labeling that horizontal line. So we just say, well, let y equal k, where k is in real numbers, be any horizontal line. It's just, we need something to work with. Well, if any and all horizontal lines strike f at most once, then f of x equals k has either no solution. This would be the case where the horizontal line does not strike the curve f, or only one solution. That would be the case where the horizontal line does strike the curve f. Now, a theoretical piece that can be kind of confusing to people is this. If f of x equals k has no solution, then k is not in the range of f, right? F of x cannot become k, therefore k is just not in the range of our function f. And if that's the case, there's no need to talk about the inverse function. So the case where we have no solution, I'm not even going to talk about that because I think that's going to lead to deeper, darker details. So instead, I'm just going to deal with what if it only has one solution. So if f of x equals k has a solution, and in that case, it would only be one solution by our assumption, this means that the output of k leads back to only one input from the domain of f. That output of k is in the range of f, and it leads back to only one input from the domain of f. Since k was arbitrary, this means every output for f leads back to only one input. Or I shouldn't say every, I should say each output of f leads back to only one input. And I've summarized that down below in that sentence. Since k is arbitrary, each output of f leads back to a single input of f. And that, by the way, that word arbitrary tends to throw people off. So what I'm saying is, I didn't tell you what k really was. So k could be any number. It could be any real number. So because of that, every single possible output for f, every single element in the range of f, each of those elements leads back to only one input. So graphically, it kind of looks like this. You have this domain for f, and you have this range for f, and we've just shown that each of these elements in the range of f lead back to their unique friends in the domain. They don't lead to two things from the input, they only lead back to one each, and they're unique items. So that is what I'm trying to say to get you to understand there. Well, if you read that sentence, if I told you I have a function, well, immediately when I state the word function, you know that each input leads to a single output. And you should know, up to this point, that for a function to be one-to-one, each output needs to lead back to a single input, and guess what we have just written? Each output leads back to a single input. So thus, we have shown that f is one-to-one. And that's where we wanted to arrive at in this second proof, second half of this proof. We wanted to assume that we had any and all horizontal lines intersecting the graph at most once, and we wanted to arrive at f must therefore be one-to-one. So that's both halves of the proof, and for the most part, I don't really do an example of these because they're very fast and most people are excellent with them. If I give you a graph like this, here's a horizontal line, it strikes it more than once, it is not one-to-one. It's a function, just not one-to-one. So that's the horizontal line test. Generally speaking, I say this in calculus, that as you advance through mathematics, the theorems get easier to understand and harder to prove. Whereas the opposite early on in mathematics. Early on in mathematics, the theorems you're handed don't make sense at all, but the proofs are actually easy. You guys are at this cusp where you have proofs and theorems that can be both challenging. So anyway, this is not something your professor would expect you, hopefully, to prove in class. That would be no fun, but it's good to see these. And every time that you see one of my videos coming up that where I say we're going to prove this, you should try to sit there and really try to digest and watch the logic of what's happening. Anyhow, all right, that finishes out a review of functions for a college algebra student. Have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close. too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.